Okay, I got a few more homework problems. I kind of gave us some other problems this week, not just problems on the incline plane. Some of these are kind of throwbacks to previous content, but that's all applicable to what we're doing. So let's see. So I'm going to go through these. All right, this problem is for an object that's pulled at an angle. Remember, we talked about those during the first part of this unit. So we've got a 5 kilogram box on a rough surface being pulled to the right at a constant speed. So that might be important. By a string that's at an angle of 30 degrees, and we have a mu value, and we want to know tension. So we actually want to know this, like the hypotenuse here of our tension force. Okay. So let's go ahead and do a few things that we know. We can get Fg, and that's going to be 5 times 9.8, so that's going to be 49, I think. Okay. We know that we're moving along a surface. So in the case of this scenario, we're going to have components of tension. Okay, we're going to have like a tension Y and a tension X because we're at an angle. So we know that our normal force plus our tension Y has got to equal our Fg because these two are going to balance this one. Okay. So I'm going to go ahead and substitute in a couple of things here. I've got Fn plus, I'm just going to put in the equation for Ty. It's going to be T, which is what I want to try and figure out how to get T times sine of 30, because Y is my opposite side here, equals 49. Okay. So I want to try and get T, and I don't know T. I also don't know Fn. So let's see if there's a way for me to figure out Fn. I'm told that this is at a constant speed, and that means that I am not accelerating, and so that means that my F net is going to be 0. So I'm going to set up an expression for F net and see if that will help me. I know my net force is going to be my Tx component minus friction. Okay. So I'm going to have T cosine of 30 minus 0.3 times normal force, and that's going to equal 0. Okay. Because, again, I'm at constant velocity or constant speed. So what I'm going to end up doing here is really getting another expression that I can substitute into this first one. I don't think we've done a whole lot of problems this way. This is a problem-solving strategy that could come up if you're missing like two things that you need to figure out. Okay. So let's see. Cosine of 30 is, oops, I'll put my calculator was on. 0.866. So 0.866 minus 0.3 Fn equals 0. 0.866 equals 0.3 Fn, because I'm just moving this around to the other side so that I can solve for normal force. Oh, and this is multiplied by T. I forgot to carry my T down. I don't know T, so I got to keep it in there. So T times cosine 30 minus mu times normal force is 0. That's my F net. And those are balanced because I'm at a constant speed. So then I'm just doing cosine of 30 here. And then I'm moving this to the other side. And then I'm going to end up with Fn equals 0.289, just when I divide that by that, times T. Okay. So now I can put that back into my first expression. Okay. I'm going to go back up here. And I'm going to substitute point. Kind of running out of room. I'm going to flip over to the back right quick. I'm going to have 0.289t. That's my normal force. Plus, let's see what the sine of 30 is. .5 plus 0.5 times t. Okay. So I'm just converting that to a number, equals 49. And now I can solve for t because everything else is stuff that I know. I mean, everything else is just numbers. So 0.289 plus 0.5 is 0.789. Wait a minute. Hang on a second. Oops. Okay. I made a boo-boo. This is not 0.289. This is 2.89. It's like, that's not right. Okay. So 2.89 plus 0.5 is going to give me 3.39t equals 49. And then I just divide both sides by 3.39. And that gives me 14.4 for my t. So we kind of had to do a bit of substitution and using the fact that this was at a constant speed to our advantage there, right? Because otherwise we wouldn't have been able to figure this out with the information we were given. But we knew from the beginning that the F net would be 0, because so we could use that to our advantage setting this up. And then we also knew that in the y direction, our forces are balanced. So we use that to our advantage also. So hopefully that one makes sense. That one's a little different maybe than some of the others we've done, but you're not necessarily going to get a question exactly like every question we have done. So it's good to do some other different ones. So, okay, so let's look at, see, in the interest of time, let's look at this bottom number 5, and then I'm going to go back in the next video and do number 4, because it's a little longer. Okay, object travels down a ramp, so like an incline at a constant acceleration. It experiences a force of friction and a gravitational force. Which of the following could be true about the motion of the object? Okay, so looking at these choices, we can eliminate D right away because force of friction is not going to act in the same direction the object travels. It always opposes motion. So I'm going to X that one. Okay. Let's see. If the object increased in mass, so if its mass increased, the normal force would remain the same. We know that that would not be true because our normal force equals our force of gravity, y, in the case of an object on a ramp. And mass is part of that. That's going to be m times g for the y piece. It's going to be m times g times the cosine of that angle. So mass is part of, it's embedded in normal force. So that one won't be the same. All right, if the object increased in mass, the object's acceleration would change. Let's think about that for a minute. We know that mass and acceleration are linked together, right? But we also know that for our incline, our net force is generally going to be our FGX minus our force of friction. And so if we just expand those out, let's use m times a for our F net. That's just Newton's second law. Then I've got mg sine of theta for my FGX minus my force of friction is going to be mu times normal force, which is mg cosine theta. Hopefully you can see pretty quickly that mass is going to cancel out here because it's in all three pieces of that equation. So even if it increases in mass, that the ultimate F net and acceleration aren't going to change because mass is part of all of these pieces of this here. So it cancels out. So that leaves us with A. The force of friction between the surface and the object is less than the component of gravitational force. And that's what happens when we're traveling down a ramp at an acceleration. We end up with a force of gravity x that's greater than our force of friction. So friction's taking some of that away, but it's not keeping us from traveling down the ramp. Okay, probably one more video on these homework problems. So that answer was A.